Oh, hey, we're going. Sorry about that. That's kind of weird. Anywho, so we're going to chat about Markov chains. So Markov chains, the big idea here is that you have probability matrix. So our matrix, we're going to start off with n by n, and there'll be a matrix full of probabilities. Because the probabilities, of course, they all are between 0 and 1. That is all of the entries between 0 and 1. You can do it any number of ways you want to. Okay. You can have it so that the probability of, in essence, starting from here and finishing here goes in a row. The one I'm going to do tonight, I'm going to start here and finish here. I'm going to start on the top, and I'm going to finish at each one of these locations, so that the sum of this column will be 1 each time. Now let me demonstrate what I mean by that. So what I have here is 4 towns near where I grew up. So this is the probability you start in Walla Walla and you finish in Walla Walla is 29%. You start in Walla Walla, you finish in Dayton 30% of the time. Start in Walla Walla, finish in Waitsburg 40. Start in Walla Walla, finish in Starbuck 1% of the time. Start in Dayton, finish in Walla Walla, start in Dayton, finish in Dayton, start in Dayton, finish in Waitsburg, start in Dayton, finish in Starbuck, etc., etc., etc. Okay, as you can see, the sum of each of those columns is 1. Okay, that'd be weird if it's anything other than 1. Okay, now let's think about what that means. What if, in this case, what I've done is I have said, well, first of all, let's look at this. Okay, so if there was 2,000 these little reusable containers, let's say, shipping containers. I own auto parts stores in these 4 towns, and I ship, I transfer stuff between my stores in these containers. And initially there was 2,000 in Walla Walla. Let me go ahead and type this in so you can see that. And initially there was 2,000 in Walla Walla. There was 500 in Dayton. 300 in Waitsburg. And 200 in Starbuck to start with. And there you go. Now, cool, nice. Now the question will be, is this is on initially, so I guess you could say initially, or if you want, day 0. A good way to think about that. Okay. So day 1, where will they be? Now, let's think about this for a minute. Now, to end up in Walla Walla, okay, what did you have to be? Well, you could have been in Walla Walla and finished in Walla Walla. So a little probability lesson, kids. When you hear the word and, it always means multiply. And when you hear the word or, it means add. That's always true in probability class. Okay? So you could have been in Walla Walla and finished in Walla Walla. You could have started in Dayton, or you could have started in Dayton and finished in Walla Walla. Or you could have started in Waitsburg and finished in Walla Walla. Or you could have started in Starbuck and finished in Walla Walla. How did I do that? Well, so if you started here, okay, there was 2,000 initially, and 29% of them ended up in Walla Walla. Cool. Dayton, let's look at that. Dayton, if you start in Dayton, there is a 70% chance you went to Walla Walla. Well, there's 500 initially in Dayton, times 0.7. Waitsburg, there was 300 initially, and Waitsburg, Walla Walla, 80%. And Starbuck, there's 285% went to Walla Walla. Nice. Let's get a calculator out. So 2,000, by the way, I was doing this math earlier, and I typed in 200, and I got a very strange answer, and it took me a while to figure out why I got a strange answer. And then I almost did it again. Done. Holy buckets. So somewhere along the line, you dingbat, you didn't get a decimal in there. Oh, you didn't put a plus sign. There, you knucklehead. Now, plus. Boom. Look at that. And I still screwed something up. So let's try that again. You ding dong. So, oh, for God's sakes. Try it again. So 2,000 times that, and then plus 73 times 500, you knucklehead. There you go. Good Lord. What is going on? Oh. Plus. Let's try to do this right, Jay. There you go. 500. What is going on? Oh, because it's 300 in Waitsburg. Boy, been a rough day, friend. Oh, for God's sakes. How about you hit the 3? Okay, that's closer. I'm still not 100% sure that I'm right. So 2,000 times 29. You know I'm going to do it in Excel because at least I can see what I'm doing over here and I don't feel like such a friggin' idiot. All right, so listen. If you are going to end up in Walla Walla on day 1, you either were in Walla Walla the previous day and finished in Walla Walla, or you were in Dayton and you finished in Walla Walla, or you were in Waitsburg and you finished in Walla Walla, or you were in Starbuck and you finished in Walla Walla. Good Lord, that is the correct answer. I don't know what took me so long to get there, but whatever. You're like, Jay, I feel like, well, don't answer yet. What if you're in Dayton? Well, listen, you're either were in Walla Walla and you went to Dayton. So that'd be, so you were in Walla Walla, so that's here, times Dayton, yes? Plus, or you were in Dayton and you went to Dayton, or you were in Waitsburg and you went to Dayton, or you were in Starbuck and you went to Dayton. Wait a minute, Jay. Aren't you literally just taking this matrix times this vector? Oh, you're right. I didn't think about that. So watch. O equals m mult. Now this is what you can do in Excel if you like, because I'm already here, or you can use your calculator. I will show you the other way in the calculator as well. Close your parentheses and you must hit Control Shift Enter. Bam! And there you go. You're like, whoa, that was cool, Jay. Do it again. No, I'm not gonna do it again, but I'm just gonna like show you that there it is. Now, what about, oh shoot, what about day 2? Well, you'd be the same thing, because if you're gonna end up in Walla Walla on day 2, well, you would have been in this. There's 1,340 in Walla Walla on day 1 times 0.29. Wait, so you're saying literally all I have to do is go equals m mult of this matrix times, oops, comma, this vector here. That's correct. Wait, but isn't this vector this matrix times this vector? Wait, yes, indeed it is, sir. Wait, so you're saying, I can just keep going. Yeah, wait, what's going to happen over time? Well, over time, out somewhere around day 100, it's going to be kind of interesting. Now, remember, what do you got here? Well, in this case, you've just got, you just have this first column is all you've got, right? Well, you've got this matrix to the 0 power, which is 1 times this guy here. Cool. Day 1 is this matrix to the first power times this guy. Day 2 is this matrix squared times this guy, and so forth and so on and so forth, all the way on out. So if you're out here at day 1,000, okay, well, you're going to have your initial matrix, I'll call it A. So it's going to be A to the 1,000 times your vector, right? Which is this vector here, right? And you're like, well, that'd be cool if there's a way to automate that. Well, there is. Okay, there's two things here. There's two ways to talk about this. So, can I automate it? Absolutely, I can automate it. Okay, that's number one. And then number two, is there a way to like find out like where it goes to as you go to infinity? And the answer to that is absolutely. Okay. So what's going to happen here is this. When you look at this, it's going to be quite clear that when I do this all the way across, you're going to see that it's, obviously it's going to be this row times this column. It goes right here. This row times this column goes right here, and so on and so on. Okay. Excuse me. All of these columns had better add up to what? It better be 3,000. So I always have 3,000 containers floating around. This is how many should be there. Quite clearly, there's not a decimal version of them floating around. I know that. You know that. This is a predicted value. Just like it's predicted that, a family in America will have, I don't know, 4.5 children, 4.5 dogs and 2 children or whatever it is, okay? So similar process to that. Now, what's going to be interesting is this, does that original matrix, does it have eigenvalues? And in fact, it does. And in fact, this Markov matrix will always have lambda equal 1 for one of them, 100% guaranteed. The rest of them, all other lambdas less than 1. And specifically, the absolute value less than 1. Okay? Meaning that they can be anywhere positive or negative, but they're decimals. This is a big deal. That is a huge deal. Okay? Now, something else that's kind of interesting is this. You can always take any matrix, let's call it matrix A, and you can always write it like so. Where this is V, this is your eigenvectors as a matrix, times, we'll call this big, oops, not A, you jackass, big lambda, this is capital lambda, where they will be on the diagonals, lambda n, zeros everywhere else. Okay, in other words, it's not just one lambda times the identity, but that's the idea, is all the different lambdas are on the diagonal. And then this guy here is going to be V inverse. Okay? You can always write it like that. Okay? Well, why do I care? It's a good question. I'm glad you asked. What would A squared be then? Well, it would be V lambda V inverse times V lambda V inverse. Wait. Well, that's interesting. What does V times V inverse give you? The identity matrix. So wait, so it's just going to be V, this guy squared times this guy? That's right. Wait, I'm sorry, not that guy, you jackwagon, this guy. Wait a minute, so are you saying that when you do this problem, the eigenvectors just get squared? That's correct. That is exactly what I'm saying. So when we do these problems, okay, and you're going to be talking about multiplying through these guys, what's going to end up happening is that you're going to end up with, when you get out there ways, you're going to have this guy to the k power, this guy to the k power, this guy to the k power, right? Now, all of them are less than 1, so they're all going to tend to 0, except for this guy, which one of them is going to be 1. And what does 1 do when you raise it to the any power? It's going to stay 1. That's going to be a big deal, okay? Because when we see this, now we're not going to go ahead and break these out, okay? But suffice to say that A to the k power is always going to be this, okay? And so the idea is that when we see this, we're going to keep multiplying by the same vector again and again and again and again. I mean, matrix again and again and again. What's going to end up happening, okay, is that you're going to end up multiplying these guys through. And as you go to infinity, these guys will go to 0 because they're going to be things like 0.5, 0.3, what have you. They're going to go to 0. But 1 to the any power is always going to be 1. Wait, so there's going to be a steady state solution, Jay? We're going to be approaching steady state over time. Yeah, exactly. over time, that's where things are going to end up. I was talking to a guy the other day. We were discussing things. Person doesn't really understand about AI at all, has no idea about how it works. And he was saying how he wished that computers and robots were the police. And I went, huh? He goes, yeah. And I said, how's that now? He's like, yeah, because if computers were in charge, then there'd be no way that anybody could say that there was any kind of race or this, that. And I'm like, what? And he goes, I said, well, when you program the system, what are you going to program for? Like quick response times and things like that. He's like, yeah, probably, yeah, and some other things. I'm like, okay, yeah. So so you're going to start off with cars spread out all over town. And when the computers are in charge, once it starts getting data, what's it going to do? It's going to start moving cars to positions where they can respond faster and faster and faster in units to moving. And so there's going to be hot spots in Portland, for instance, where the hot spots are going to be. And that's where the cops are going to be. And as a result, whether the robo-cops or normal cops, doesn't matter. That's what it means. He's like, no. Someone had to program it that way. I'm like, yeah, you programmed it for quick response times. So I can't have them equally spread over town. They're going to end up going there. In other words, that's what we call a steady state solution. And over time, that is where things are going to tend to be. Okay. And of course, by the way, I have friends that are police in different parts of the world, different parts of the country. And they say things like that. Well, we're seeing a rise in crime here. So what does everyone do? Well, the police chief in that town still, the other towns, they move them over there, move more cars over there, obviously to address the crime. And it takes care of it for a while. And then what happens? Well, then it moves, obviously, and things move back. But that's the difference is that what's happening over time in those situations is because the police made a change, then the other people made a change. We're saying if nothing changes, okay? So if nothing changes, it's going to move towards a steady state solution. If I deliver packages between my 4 stores in the same idea, same direction, same whatever, then I'm going to have it approach certain values as I get there, right? Now, question is, let's bring this baby up here, and let's go ahead. I'm going to put it in the calculator because I feel like it, if you don't mind. So I'm going to do a couple things. First, I'm going to punch this baby in. And so 0.29, comma, 0.7, comma, 0.8. By the way, as I said before, I think in class, you can you could start on the left and then go to the one on top if that makes you happier. I chose to go this way this time. Doesn't matter as long as you're consistent. The difference would be if you do that, instead of multiplying by the vector afterwards, you do a row vector times your matrix, and you'd end up that way. So you have to be a little bit careful in how you go about it, how you go about multiplying. Yeah, you have to go about it a little bit differently in terms of your multiplications. 0.4, comma, 0.16. Okay, and let's go find the eigenvalues of this guy, huh? Eigenvalues. And boom. Now you're like, uh-oh. Now, look what happened. Look what happened. Look what happened. Something's a little screwy there. Okay. See, one of them is a little bigger than 1. That's an issue. So what does that tell me? It tells me that J screwed up somewhere. Let's see if J can figure out what J did, because J's an idiot. I'm gonna pause you for a minute, I think, while I go cogitate my stupidity. Oh, it's 0.04, you goober. All right, so let's try that again. It's kind of a big deal that your stuff gets put in correctly. Okay, if you don't get it put in correctly, it will not hold true. It's weird how that works, you know? I mean, I feel like I should do it like any way I want to, I feel like. Wrong. There you go, by God, I told you, get 1. Kaboom! There they are. So you got negative 0.45, you got 1, you got negative 0.057, and you got negative 1.139. I think I jotted this on my paper over here. I'm going to double check that I wrote that down correctly. Yes, that is what I wrote down. Good for me. Good enough for government work anyways. All right, now, what I'm going to do is come back over here. I'm going to find my eigenvectors as well whilst I'm here. And there's my eigenvectors. Oh, what the Sam Hill does that even say? Eigenvector. What just happened? I don't know what I just found, but I don't think that's really a thing. Huh. Huh. Delete. All right, let's try this again, Mr. Groom. You big dope. All right, grab this guy here. There you go. Come back over here, you ding-dong. Wait, what just happened? Oh, go up here one more. Sorry, my bad. So go over here to the front and come back over. Oh, for God's sakes. Clear. Let's try this again. There you go, stupid. You big ding-dong. There you go. Come on, now let's come back here and let's put in just the C. See? Kaboom! It takes a while, by the way. It's a tricky problem. There you go. Yeah. Okay, cool. These are in a different order than I got them last time, but that's cool. It's the same ones I have from last time. I hope so. Now, the first one goes with the eigenvalue that it gave you first. So the first one it gave you was negative 0.057. That's that first column. The next one over goes with 1, and so on and so forth, and so on. Okay? Now, yes. Really? I remember that being negative last time. Ugh. Oh, no. Wait. What just happened? Oh, no, never mind. There we go, No, we're okay. Okay, so the first one's negative 0.45, right? And then the second one is, yes, okay, so then the second one is 1. And then, how crazy is that? Oh, okay, don't freak out, Jay. Don't freak out. Whew, don't freak out. I was just going to say to myself, Jay, you big dope, you screwed something up, but be careful before you cuss yourself out here. Why are all of my negatives wrong on some of these? So, for instance, on number 1, on the one for the second row over, I have that they're all positive. This thing has that they're all negative. Is that a problem for me? No. Because remember, that's just a vector that's going the... Oh, shoot. Judas Priest, shut up. Anyway, remember, all that's saying is it's going the opposite direction. It doesn't change anything. What I will notice later on is that we're going to get a constant. It's a slightly different constant than I had previously. So mine previously, when I worked it on my paper, let's say it would have been negative 50 or something. In this case, it's going to be positive 50. It's going to be opposite sign of whatever I had before. Okay? It'll all come out in the wash, I promise. Okay? Now, here's the fun times. Okay? Here is the fun times. So this matrix that you see right here that we're staring at, do you see it? This guy right here, this eigenvector matrix. Cool. That is my V, by the way. So I'm going to do this real quick. I'm just going to hit this guy here like so. And I'm going to go times. And I'm going to add a new matrix in here. And my new matrix is going to be 1, 0, 0, 0. Now I'm demonstrating this so that you can see how this works. That I can then write it in this fashion. I just want to show you this. Again, it's more of a, wow, that's cool, Jay. Thanks for showing us that. Oh, wait. So 0, comma. Oh, crap. I got to do them in the right order. You ding dong. So they were given to me as negative 0.45, comma, comma 0, comma 0, comma 0. 0, comma 1, comma 0, comma 0. It's a big deal that we go in the order in which they were given to us. Let's go up here and look. I can't remember. And then negative 0.057 and negative 0.14. So negative 0.057, comma 0. So this is my big lambda matrix, and then 0, comma 0, comma 0, comma negative 0.139 times, this is exciting, times this matrix, up here to the -1. Now, if I cross my fingers and like tap on, whatever, what I should end up with is what I started with, which is 29%, 30%, 40%, and 1%, roughly. You see that? And so obviously it's going to be a little off. I rounded. That is exactly what it should have been. Okay. Now, why do I care? Okay, well, again, if you square this, okay, if you square this answer that you just got, so it's squared, okay, that is the same thing that I would have gotten if I had just gone back up here and gotten my original A, which is, okay, is that my original A? No, that's the wrong one, dummy. This is my original A right here. And I'm just going to get rid of this eigenvalue crap and just square the thing. And there you go, 0.62, whatever, 0.62. Obviously off a little bit for rounding, but that's kind of a neat deal. Now, the reason I mention that is not because I want to square things that way. No, in fact, that's disgusting. But the thing that I want to point out to you is that when you keep squaring, the eigenvalues of A squared are the eigenvalues of A squared. The eigenvalues of A to the K are the eigenvalues of A raised to the K power. Okay? So that'll always be true. That's a big deal. Okay? Because what happens in these Markov chains is you're going to keep multiplying by your A matrix a gazillion times. Okay? Now, interestingly enough, you're like, Jay, show us more. Well, I'd love to. So what I'm going to do here is I'm going to raise this thing, that's my original matrix, to the 100 power, and then times it by my original vector, which is 2,000, comma 500, comma 300, comma 200. Now, I put that in as a row vector, so I'm going to transpose it and cross my fingers that Betsy doesn't tell me to go fly a kite. And I should get out a 4x1 vector here in a minute. And this is where how many containers will be where after 1,000 days. And what you'll see is that 1,000 is awfully close to, in this kind of thing, let's say you have 300 days a year of business operation or whatever. Why, that puts you at 3.5 years, 3 and a little bit of years, 3 1/3 years or something of operation. Well, that's about as close to infinity as a guy needs to get, to be honest with you, okay? You're probably not a lot going to change after 3 years and whatever of this transportation business, okay? Now, Betsy's a little clogged up. I'm going to go ahead and hit on to break the program real quick. I said I was. Come on, break. Oh, boy, I pissed her off now. Come on. All right, give it to me. Here we go. So what you can do if this ever happens to you on this emulator, which is, by the way, pretty slick, you just hit, no, stop it. Seriously? Well, uh-oh. No, now what's going to happen? I'm going to reopen it, and it's going to still be going. That's going to piss me off. Oh, it's still going. I wonder if I can do this while it's running. I don't think I can. I'll try it, though. Break. Oh, now you broke. Okay, whatever. Hang on. So now I'm going super fast speed. Let's try this. So I don't know if this will actually work on the computer or not. By the way, oh, boom, there it is. Okay. That right there, my friends, is, oops. Now that's what happens when you unrestrict the speed. It shuts off because it was going to run the battery dead because its clock runs faster now. So after 1,000 days, there should be 1,500 cartons of these cartons in Walla Walla, 591 in Dayton, 731 in Waitsburg, which is kind of weird. I don't really understand that. Well, I do, but I don't. And then Starbucks, 118 of them. Okay, whatever. Again, this is just an idea of what's going to happen over time. Okay, now you can't necessarily see what's going to happen over time, but you can see that Walla Walla is going to get smaller. Okay. By the way, each day, look at this, 100% of the population of Walla Walla leaves Walla Walla. You see that? 29% come back in from Walla Walla. Dayton, 100% leave Dayton every day. 4% find their way back every day. Waitsburg, 100% leave, 2% find their way back. Starbucks, everybody leaves. Ha ha! And none of them come back to Starbucks that were in Starbucks today. Why would that be, for instance? Well, Starbucks is way out there, let's say. Well, it is kind of way out there, but let's just say that the truck went out there today and it dropped some stuff off and then it came back. Well, if it only just came back, then any carton that started out there would never get back to there. Does that make sense? It would never get back there. This is very similar to what I was thinking about when I did this problem, was actually thinking about our local Napa store. It is owned by the outfit in Beaverton. They own Beaverton, Forest Grove, Hillsboro, Castle Rock, Longview, St. Helens, Scappoose. I think there's one more. And the truck comes in from Castle Rock in the morning, stops in Longview, picks some stuff up, comes to St. Helens, Scappoose, goes into Portland, picks up some stuff, I think, swings over the hill, and then pretty much the rest of the day goes back and forth between, gosh, I don't know, St. Helens. I think it goes back and forth between St. Helens, Scappoose, and one of the Beaverton stores, I think. And it's just back and forth, back and forth. And then at the end of the day, she heads back over to, I think she gets to Longview in the afternoon for a minute. Then she comes back, a couple more passes, and then at the end of the day, back to Castle Rock. Okay? So it's possible, although not likely, that something that started in Castle Rock would get back to Castle Rock at one of the crates. Okay? Because it's at the end of the run. All right? It's the start and end of the run. Okay? It may or may not ever get back to them. Okay? But if you started in St. Helens, you might load up one of these crates full of parts. It goes to Scappoose, gets dropped off, this and that. She'd run some errands. They come back, and they've loaded up that crate again with more parts that are destined for St. Helens. So it may end up getting back to there. At the end of the day, it's musical chairs. That could end up being repackaged and sent to Longview. Or something. The point is, this is the kind of thing that happens. Over time, though, each store should have a certain amount of these crates laying around for shipping purposes because, obviously every night they put in orders. And so, like, if you're in Scappoose, you see that St. Helens has this part, you can order it from them in the morning, and it gets just shipped back and forth and back and forth and back, because that's just part of the game. And, of course, the big distribution center as well. Now, that's all fine and dandy, Jay. So is there a shortcut besides getting a calculator and then supercharging the thing? Actually, yeah, there is. So what a guy can do is write it out thusly and say, listen, I want to know, typically the big kids write U sub k is equal to, now this is how they write this, they write C I lambda I x I. And it's the sum of these guys. I goes from 1 to n. Okay, Jay, what the fink does that mean? Oh, well, okay, well, let me clue you in there. So what's going to happen is this, okay? So U sub k, so like say the 1000th day, is going to end up being something like, oops, so sorry, I forgot my k part right there. U to the k, there we go. Forgot my k, there it is. Don't forget your k. Is going to be then C1 lambda 1 to the k times x1, C2 lambda 2 to the k x2, C3 lambda to the k x3 dot 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 Cn lambda to the k x to the xn. Okay, well, what in the fink is going on here? Okay, these are your eigenvectors. Obviously, those are eigenvalues. Why are they squared, or to the k power? Because, again, on the kth day, we will have multiplied by a k times, meaning that you'll have lambda to the k power. What is c? C is just a constant. We're going to figure that out in momentarily. You will see what I mean by that. Okay? So, pretty straightforward, pretty easy to do-ish, and away we go. Okay? Wait, so what you're saying is, Jay, is that u to the k is going to be equal to c1. I'm going to write them in this order. 1 to the k power Now, this is what I have written down on my paper. I'm not going to go look at the calculator again. And if you wrote them down before, or you're looking at them before, you'll note that mine are opposite, I think, sign. Actually, I might go double check this one because I might have made a boober on that one. I don't want to mess it up. Yada, yada, yada. Criminy. Let's get up there, babe. Eigenvectors. There they are. Okay, so my eigenvectors are negative, 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 negative. Mine are all positive. Hot diggity. Okay, good. Plus C2. And then my next one over is this negative 0.45 to the k power. And then times, again, this is just the way I have them written, 0.75, negative 0.36, negative 0.53, negative 0.13. I think that's what that says. Let's go look again. Positive, negative, negative. No, negative, negative. Wait, what? No. Wait, what? Oh, the bottom was positive. Sorry. There we go. Let's fix that. There we go. Plus C3. Next one over is negative 0.06, I think. To the K. And then his vector that's associated with that is, I don't remember which one is which. So, oops, come back, come back, come back. Okay, negative 0.06 is the third one over. Yes. So the third one over, and that is 1, 2, 3. So the 0.047 one. Okay, so correct. Okay, so 0.047. And then basically 0.1, negative 0.77, and 0.63, we'll call it. Okay, close enough for government work. Again, we're just trying to get the idea of what's happening here. And then negative 0.14-ish to the K. And of course, that's going to be 0.28, negative 0.77, negative 0.08, and 0.57-ish, basically. Good enough, okay? This is our equation. Now you're like, Jay, how in the devil are we going to find our K? It's a good question. It's a good question. But before we get to that, let me just suffice to say this. When K goes to infinity, as K, what are you writing? As K approaches infinity, you will be left with this. Does that make sense? As K approaches infinity, you'll only be left with this because this guy will go to 0. So will this guy, and so will this guy. And so we'll take those with them. Okay? Now, anything other than infinity, I'm not going to be doing that. But, okay, I'm just going to go ahead and just kind of demonstrate this. Now, how am I going to get C1 and C2 and so forth and so on? That's a good question. So, to do that, what I'm going to do is the following. Okay? I know that initially at K equals 0, there were 2,000, 500, 300, 200. Right? That was the initial value. So what do you end up having? Well, you end up having 0.85 C1 plus 0.75 C2. There's going to be 4 equations with 4 unknowns. But you're like, wait, Jay, there's an easier way to do this. You're absolutely right, friend. If you look at these guys as a matrix, wait, I have that matrix. That's right, you do. To the -1 times this vector, you will get your coefficients that you seek. Okay? So what I'm going to do is go in my calculator here. This matrix, well, I'm going to come down here real first and clear some room out because it's freaking me out. All right, clear, clear, clear. Where are my eigenvectors? There they are. So I'm going to grab these dudes, okay, and I'm going to clear this out like that. So I want just the matrix. Oh, wait. Oh, fiddle faddle. I lied to you. Don't do that. Let's get the eigenvectors again. Here they are. Okay, so there's my eigenvectors coming up right now. Boom, there they are. Okay, so I'm going to take this answer matrix right here to the -1 times, and I'm going to put it in again as a column, a row vector, and then I'm going to transpose it because it's easier, I think, but maybe you don't think so. Okay, so these are my C1s. So 641. What did you screw up this time, Jay? One moment, please, while I figure out how I screwed the pooch on that one. Just a second. Oh. Crap. Crap. Crap, crap, crap. Crap. That's not going to work in that order because it's not going to work in that order because I don't know. I'm going to pause you. Something went wrong. I know what my... Okay, so it's important that I put them in the wrong... See, I moved this eigenvector here. I moved it. I swapped these two. Okay, so it's important you get them in correctly. So I went ahead and reordered them in. So what I have as C1 is 1843. 1843. 625, I think I said. 154. And negative 155. Okay. Now you're like, okay, well, so what do you want to do here, Jay? Well, okay, let's find out. So for instance, if I were to use this guy, what I could do is I could come back in here and I could say, well, okay, let's try this. So if you think about this, in this situation here, so it's just going to take, let's say you plug in to the 100th power, for instance, okay? It would simply be a matter of taking and plugging into this calculator, and whatever comes out, comes out. Now you're like, is there an easier way to do this? How many numbers should I get in this case when I'm finished? Okay, I should get 4 numbers, correct? That's what I'd like to get. And I'd like to have one that occurred for Dayton, Walla Walla, Waitsburg, and so forth, correct? And so I feel like I'd like to get this guy when I'm finished, yes? That is, I'd like to get a 4x1, okay? So how am I going to pull that off, you ask? Good question. So when I look at how I'm going to do that, let's see, how would I go about doing that? What's an easy way to do that? Well, I don't know if I can think about how to do that real easy. Hang on a minute. Yeah, let's don't do it that way. So let's just think about it. So we could do it that way, or you could just plug it in. Now, obviously, a guy could type this in, and you can see it all out, and then it's just adding all the way across. Not very hard. Plug 100 here. 1 to the 100 is 1, obviously. And then so it's going to be 1843 times 85%, and so forth, and so on and so forth. And then you get 625, negative 0.45. It doesn't take a brain surgeon to see that this is going to be very small. For instance, to the 100th power. Okay, for all intents and purposes, that's 0, am I right? Times 625, Jay. Okay. It's still basically 0. Okay, but then times it by 0.75, then see what happens. Yeah, it's even smaller, dude. So as you can see, these go to 0 rapidly. The only thing that's going to be left, in essence, is this guy here. And so, in fact, when you look at this, you're like, oh, wait, so even if it was to the 100th power, it's not going to make any difference. So if I do this, it's going to be 1843 times 0.85. And that's for Walla Walla. And then 1843 times 0.32. And 1843 times 0.4. And 1843 times 0.06. Let's see what the calculator thinks about that. 1566. I seem to recall that number. Okay. 1843 times 0.32. 590. I seem to recall something along those lines as well. Okay, 1843 times 0.4. 737. If you recall, that's true. We did have more in Waitsburg. And then, of course, this is rounded a little bit, so just don't be panicked about that. And 110. Okay, does it still have to 3,000? I bet it's awfully close. 1566 plus 590. Obviously, we're rounding. 737 plus 110. Yep, how about that? We're awfully close. Okay, nobody's really panicking about that. Okay, now, again, up here, if I didn't delete it, I can't remember if I deleted it or not. I can't remember. I think I did, didn't I? Oh, rats. Well, let's do this. I don't remember where it went, but I'm just going to come up here and do that. Okay, where's A? Is this A? That's A. All right, I'm going to come down here. Get rid of this. I'm going to do that same matrix calculation just one more time so I can see what the exact value is, and then we'll compare them to the approximated value. Now, the cool thing is that because you know this approximated value, okay, at infinity, this is what it's going to be, awfully close to it, okay? So I'm just going to go ahead and plug 1,000 back in times this. And as we said, 1,000, there's really no difference between 100 and 1,000 in terms of this, okay? There's almost no difference. There, and then emulator options, unrestrict, go. And so what you'll find is that the actual value is 1554, 591, 735, and 118. That's good enough for what we're doing here, okay? So that's what's beautiful. And again, of course, if you were getting really exact, I wouldn't round at all. But this is how you would do it. Okay? If you wanted it for the 4th day, I'll tell you, if it was me, I would just do a to the 4th times my vector, right? That's what I would do. Okay, that's what I use matrices. But you could also use this equation. The reason we write this equation out, the reason that we do that, this is so important. The reason that we write it out this way is so that you can see that as time goes to infinity, these pieces go to 0, and this becomes your steady state solution right here. That's the reason we write it in that format. If you want it for the 4th day, then by God, there it is, sir. That's it. That's all there is to it. Just knock yourself out. Okay, remember this is your original vector, 2,000, 500, 300, 200. Okay, nice. Now, as far as the monopoly one goes, just let me kind of draw a quick pick here. So here's go, whatever. Notice the first square. So if I was start drawing this out in my Excel, here's go. Go. Obviously, you can't go to go, so that's cool. Okay, we need a picture of the monopoly board. Monopoly board. Cool. There it is. Awesome. Let's look at a pic. All right. So the first one out is, what does that say? I can't read that. I'm going to have to make it bigger so I can read it. Mediterranean. Well, you can't land on Mediterranean, friend. It's a big fat goose egg. And how do I know that? Because all you can get on the it's a Mediterranean. Obviously, you can't land there because you can't roll a 1 on a dice. Okay, you can't do it. So what about the next one? Well, the next one is community chest. All right, cool. Community chest. Now, stop it. CC, maybe I'll call it CC1. There's a 1 out of 36 chance that happening. Okay, what's the next square? Baltic. Okay, there's a 2 out of 36. And then the next one is income tax. It's 3 out of 36, and so on and so forth. Eventually, you're going to get up here to 7 out of 36, and then it's going to come back down to 1 out of 36 when you are 12 units away. Okay, because that's the most you can get. So on the board, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So when you're on the electric company, that is a 1 out of 36 chance of happening. So electric. Okay. And then what after that? What comes after electric company? Well, everything after that, States Avenue, Virginia, all the rest of those are going to be what? 0, 0, 0, 0, 0. Don't go to sleep, computer. Okay, that makes sense? Now, what if I end, so I go around the board once and I land on Mediterranean Avenue. Well, what's the probability I go backwards to go? It's not going to happen. What's the probability I roll a dice and I land where I started from? No, I can't do that. What's the probability I land 1 unit ahead? Well, I can't do that. So then it's going to be 1 out of 36, 2 out of 36. You're like, oh, it just shifts everything down 1? Mm-hmm. And then the next one is community chest. Cool. 0, 0, 0, 0. Right? You just add a 0, right? And then it's just going to shift down. Okay? This becomes your A matrix. It's time consuming. It's a little awful. Not going to lie. All right? But you can do it. This becomes your A matrix. Hey, what will its eigenvectors be? One of them is going to be this. The rest of them, the other, how many on the dumb board? I don't even know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 40 spaces on the board. The other 39 of them, the other 39 lambdas are going to be less than 1. Okay? And the game is when you do it, you're going to get a steady state solution. And so your steady state solution, okay, now this is where it's going to be a little fun though, right? Because where did you start this time? Start on go, my friend. Like so, yes? You started on go. That was your initial value. Okay? And so when you multiply that through, okay, you're going to get so in other words, so that was your initial value. You're going to take your A and you're going to take it to the whatever power you want times this guy, and it will fill in the probabilities of where you'll be after K rolls of a dice, right? And so obviously, when you run through this whole thing, something's a little screwy with that, but that's the idea. And then, yeah, so then you can just simulate it a zillion times, and then something's a little weird there. Hold me think for a minute. Yeah. So yeah, that's what, yeah, so this is your initial place. And then see, all I did was I just multiplied my A times its initial value, right? And I just do it again and again and again and again and again. Okay, and that'd be the same thing with your ginormous matrix. Okay. Nice. Now, again, the good news is that once you find your eigenvectors and eigenvalues, the only one you really need is the one eigenvector, the one eigenvalue, the one eigenvalue is equal to 1, and the eigenvector that goes with it. That's the only ones you need of that. Okay? Because again, something like this is a god-awful mess. It was hard enough to do with the small one to the 1,000th power. If you had a 40 by 40, that's just not going to happen. Okay? But if you can find the eigenvalues and eigenvectors for it, which your calculator can do, then you can go from there. I'll pause you one more time. I'm just about done. And that's about all I got for you. So you're going to figure it out and then, see where you end up, what probabilities are. Again, you can see how that would work for Candyland, I guess. Although Candyland, you draw on the stupid cards, though. So I don't think that's going to work too good. You could do it with Candyland. It'd be a little trickier. Obviously, you can do it with, I don't know. I think the easiest one to do it with Monopoly or, is it Chutes and Ladders? I know Candyland is out there on the internet. You can find some work regarding that one. If you want some help, let me know.